Good morning, ladies and gentlemen. I hope you guys are doing well today and enjoying this fine Thursday. I'm sorry I'm a little bit, what's the term, glary here in the video today. It's really bright in here for some reason. It's a nice sunny day, so I'm a little over, the lighting's a bit off. All right, so ladies and gentlemen, today we're going to be looking at mechanical waves. And we are going to be looking at the properties of mechanical waves, what they are, how they work, and some of the calculations that are necessary to use with mechanical waves, as well as some of the properties of them. You guys ready to go? All right. So enjoy the pun. It's good. Awesome. All right. So, ladies and gentlemen, what a mechanical wave is, it is essentially a transfer of energy from one location to another without transferring matter. Okay? So, the particles within the medium or the stuff that a wave is traveling through, they're going to oscillate or move back and forth, but with simple harmonic motion. But they don't actually go anywhere. They don't move in the direction of the wave itself. So they kind of go back and forth, or they bump into something, but they don't actually move as far as that energy is going. So some examples of this are, sound waves is a classic example. Ocean waves. Okay. Earthquakes. All right. Okay. So a nice way to kind of visualize this is how energy can be transferred by matter when objects are going to collide with each other. But the transferring energy is moved farther than the matter is going. Okay. So it involves the matter transferring energy and then the matter moving more. So your example is collision of pool balls. Okay. The matter energy is transferred as the pool balls collide, but these pool balls are actually moving farther in one direction. Okay, vehicle collision is another example of energy being transferred via matter. I dropped an I there. Okay, but it's not a wave because the matter is moving without simple harmonic motion. All right. Okay. So on to our next piece. So a couple of key terms and some characteristics of waves that we need to look at. So the key term, wave propagation, it's the direction that the wave is moving as it's going to travel through the medium. Now, the definition of a medium is a material or substance. So if we're going to be talking sound waves, the medium is most often air. However, have you ever gone up on a playground as a kid and stuck your head on one of the metal poles of the playground and had a friend run to the other side and hit the other playground on the metal end of the other far side? And you can hear it? Well, in that case, the medium would be the metal of the playground. I loved doing that as a kid. I always thought it was so cool. The frequency. We've already talked about the frequency. It's the number of complete wavelengths that can pass a certain point in 1 second. Okay, so very similar idea. It's as to frequency as we used previously, the same actually. However much of a cycle can be completed, or however many cycles can be completed in 1 second. The period is the same idea. The time it takes for one cycle to be completed. In this case, one cycle is one wavelength. Okay, so we need to look at what a wavelength is for that to happen. Now, a wavelength used by the symbol lambda, I always draw lambda kind of like a crooked T. That's how I draw my lambdas. And it's the distance between two neighboring crests or troughs on a wave. It's formally defined as the distance required for the wave to repeat itself. So I'm going to pause here for a second. And I'm going to go and start labeling a few pieces on this wave down here. Okay, so the wave propagation is this way. So I need you guys to make sure you label this too. So wave propagation, that is the direction that the wave is going. So this wave is going this way. Okay, so we looked at the definition of a peak and a crest. So a peak or a crest. Well, this in the wave is either called the peak or the crest. It's the top of the wave. This is called a trough. Makes sense. It's the low part of the wave. And this middle piece here is equilibrium. Okay. Now, the definition of a wavelength, this is super important. We're going to be talking quite a bit about wavelengths here. The definition of a wavelength is the distance from here to here. So that is 1 lambda. So the distance between two peaks. Well, it's also equal to the distance between two troughs. Those values are going to be exactly the same. So the formal definition of a wavelength is how far in the wave it is to have for the wave to repeat itself, to repeat its pattern. So, well, we've gone up from the top of the wave, down to the bottom, and up to the top again. The wave has done 1 complete cycle. Here, for the trough, we've started at the bottom, gone up, and then down again to the bottom. So we could measure from any point on the wave, really. The peaks and the troughs are just the easiest ones to measure. Okay, so what I could choose, I could measure from here. I'm going to use blue here. I could measure from this point to all the way where the wave comes back to the same point after doing a complete cycle. So I could start there, go up, down, and up. Well, the wave has done 1 complete cycle and has come back to where it starts. So this distance here could also be 1 complete wavelength. It's all going to be the exact same value. All right? Okay. So the next piece is the amplitude. This is the maximum or minimum displacement from the equilibrium. So the maximum point it gets away from that equilibrium part. In a sound wave, the amplitude is a measure of how loud your sound is. In a sound wave, the frequency is a measure of the pitch. So how high or how low the sound is, that's the frequency. So this is a very high frequency, and this has a very low frequency. I hope you guys are laughing at me right now. And for volume, this is the amplitude. Okay? And this here is the amplitude as well. So to get a higher amplitude, you have to have a higher volume. So if I whisper like this, I have a small amplitude, whereas when I talk like this, I have a higher amplitude or a louder amplitude. Sounds good? Okay. So those are all properties of a mechanical wave. I think I've got them all. Yeah, I think I've got them all. All right, so these are very important. If you have any questions regarding these, make sure you see you on Google Classroom. All right, next piece. There are 2 types of waves, ladies and gentlemen. So that we are going to be looking at. So 2 types of mechanical waves. So there's the transverse wave. Now, this transverse wave is kind of more like an earthquake or an ocean wave. So the mechanical waves and the particles, so in this case, like the water or the dirt in an earthquake, are going to move perpendicular to the direction of the wave propagation. So what this means is that the wave propagation or wave motion's this way, but the particles go up and down. So think about a wave in the water. When you look at the ocean, the wave is going to go this way through the water, but the wave itself, what you see of the wave is the water comes high and then goes low, high and then low. Okay? So this is a nice little diagram here. So where you can see this here is where the particles or the water would be moving. And this is the wave or the energy, so the direction that the energy is going. And they're perpendicular. They've got a 90-degree angle to each other. Okay? So I have a dance move that I think is going to be catching into popularity. I call this dance move the transverse wave. Oh, yeah. So I need to get out of my chair here. Okay? So with the transverse wave, okay, remember, the particles are moving up and down, right? The hands, the particles. I am representing the energy. So I'm moving this way. So you do the transverse wave. Yeah, you do the transverse wave. You think it's going to be popular? Neither did my physics 20s last year. I don't understand. I think it's cool. Okay? Awesome new dance move. All right. What do you think? If you're saying, Mrs. Bray, you're weird, yes, I know. I'm shocked it's taken you this long to notice. Goodness. All right. So this next wave, ladies and gentlemen, that we are looking at is the longitudinal waves. These are your sound waves. Okay. So these are waves where the particles of matter are going to oscillate parallel to the wave's motion. So they're going to go back and forth. Okay. So the direction of wave propagation is this way, but the particles are moving back and forth. So at this one is a little bit harder to visualize because this is a set. These distances measure how far apart the particles are. Right here, they're really close together, and here they're really far apart. So we don't tend to draw waves like this very often because it's just awkward to view. So here, when these lines are very close together, that could be like the peak of a wave. And when these lines are very far apart, that could be like the trough. So a wavelength would be from here to here or from there to there. Okay. So, or what could happen is you have energy moving this way and the particles are moving back and forth and back and forth and back and forth like this. So this is your wave propagation or your wave motion. And this is the vibrations of the particles. Okay. So, ladies and gentlemen, I have another dance move for this one too. Okay, I need to get out of my chair for this one. All right. So this one is just as cool. Also, I think it's going to be popular. I call it the longitudinal wave. So, once again, I'm the energy. This is going to be where the particles are moving. The particles are moving backwards like this, and the energy is moving forward. Oh, yeah. So, you do the longitudinal or the transverse wave. I got it backwards. Longitudinal wave. Yes, you do the longitudinal wave dance move. Oh, yeah. You think it's catching? It's going to be popular? Goodness. Disappointed. My physics 20s had the same thoughts. They also thought this one wouldn't be popular. Although I think the transverse wave is going to be a more popular wave than dance move than the longitudinal. I know, I'm silly. Okay, so ladies and gentlemen, let's look at the law of reflection. The law of reflection, this is when a wave is going to collide with a surface. Okay, we're not going to do a ton with this law of reflection at this point. Something we'll talk more about in Physics 30. It's not a huge deal right now, but it's when a wave is going to collide with a surface. The wave is going to bounce off the surface. Okay, it's called the law of reflection, and it states that the angle of incident or the incoming incident is going to be equal to the angle of reflection. This is most commonly used with light waves. The normal is a line perpendicular to the surface, and we use our angles in reference to the normal line. So with this one, in an ideal medium, if I had a 20-degree incident angle in reference to the normal, well, my angle of reflection is also going to be at 20 degrees relative to the normal. Okay, so, and if the medium is ideal, amplitude and wavelength are going to remain unchanged in when a wave is going to be reflected. Okay, sounds good? All right. So, ladies and gentlemen, we have a couple of examples here. Okay. One end of a spring is attached and fixed in place to a wall. Draw in the reflected wave so that would result as the incident wave travels through the spring. Okay, well, there's our incident wave. Well, this wave is going in this way. It is coming out exactly an angle in line with the normal. It will then bounce off of the wall and it will come reflected back, looking like this, going that way. Okay? So if it's going to be coming in at 180, the wave is going to be going out at 180. You have to excuse my drawing. That is really messy. All right, that's all there is for that first one. All right, so let's go look at our second one. This one's a little tougher. The array of light is reflected in a series from two mirrors, A and B, as shown in the diagram. Now, the thing aside with this one is light is not a mechanical wave. Light is electromagnetic radiation. We got a whole chapter on that in Physics 30. Whole unit on that in Physics 30. So, ladies and gentlemen, we're only using light to practice the angle of incident. Angle of incident equals angle of reflection. Okay, so that's all we're using light for here. All right, so what is the angle of reflection from mirror B? Okay, so our goal here is the angle of reflection. Remember, ladies and gentlemen, these are, whoops, I drew that crooked. These always have to be, the angles always are relative to the normal, and the normal is perpendicular to the surface. Okay, the normal is perpendicular to the surface. So we need to find what the theta here is. Okay, well, theta here is going to equal theta here. So I would need to try and figure this out. Well, let's come over here, start over here. I have 50 degrees here. So well, that means this, ladies and gentlemen, is also going to be 50 degrees because the angle of incident is equal to the angle of reflection. Okay. Well, ladies and gentlemen, I need to figure out what this is. Well, I can't jump from here to here. But look, I have a 90-degree angle here. I have an angle here. Well, if I could find this angle, I could get this angle because of the number of the sum of all angles in a triangle is 180 degrees. I could then get that one. So I need to find this angle here. Well, this is 90 degrees. This theta, I'm going to make this theta here blue theta. Blue theta is equal to, ladies and gentlemen, 90 degrees minus 50, because that's 90 and that's 50. So blue theta is equal to 40 degrees. Okay, well, now I need to find pink theta. And pink theta, well, I have 40, and I have 98. The sum of all angles in a triangle is equal to 180. So pink theta is equal to 180 minus 40 minus 98. Okay, so with pink theta, that is going to give me 42 degrees. Well, in order to figure out what this is, I need to know what green theta is. So, green theta, well, the normal here is 90 degrees. This here, this pink theta of 42 degrees, takes up a chunk of the 90. So green theta is going to be 90 minus 42 degrees, which is going to give me 48 degrees. Okay, well, red theta is equal to green theta. So, therefore, this angle here, our goal, is 48 degrees. So, we need to put this into sig digs. We had 3 sig digs here, and so I'm going to need to add a decimal place. So, 48.0 degrees is the value of red theta. Okay, so this one is just using our angle of incident and angle of reflection with some basic geometry. Okay, all right. So, ladies and gentlemen, I wouldn't worry too much about angle of incidence and angle of reflection. We're going to be coming back to that later in next year in Physics 30. But so do some of these practice problems. It's good for you. And when you've done some of those, then come back. We'll come back to the next part of the video. So pause the video, stop it now, and then come back later. All right? We're back. I'm assuming you actually paused the video or stopped the video. So, ladies and gentlemen, we're going to go on to look at some other calculations we can do with waves. Okay? So, we're going to be looking at how fast a wave moves through its medium. So, the speed of a mechanical wave, so how fast that wave is moving, as it travels through a medium, depends on the medium itself. Okay? Now, if a medium remains constant, so as a sound wave moves through air, and nothing about that air changes, the speed is going to remain constant. Okay? Because it's going to be constant, it means it's uniform motion. And in uniform motion, we can use V equals D over T to calculate how fast or how far or how long it takes a wave to go somewhere. Okay? If the medium changes in any way, from temperature to density to anything, the speed is also going to change. So some examples, like sound waves, they go faster in liquids than in gases, and even faster in solids. So remember how I mentioned, like how you put your ear up to the metal on a playground and have a friend bang the other end of a playground with a rock? You hear it through the playground before you hear it through the air, because the speed of sound is faster through a solid than it is through the air. It works with a brick building too. So if you go and put your ear up against a brick building and have a friend go around the corner and knock on the wall with a rock, you'll hear it through the brick before you'll hear it through the air. Isn't that cool? I love that. So the speed of water waves will depend on how deep the water is. The speed of a wave when you're shaking a rope, is going to depend on the weight or thickness of the rope. And the speed of a wave through a slinky is going to depend on how tense or how slack the slinky is. So the speed of a wave, of a mechanical wave, depends on the medium. Now, this is only true for mechanical waves. It's not, no, this is also true for EMR waves too. This is also true for EMR. We'll talk about that next year. So don't worry about EMR now. Okay. So you can use V equals D over T to calculate the speed of how fast a wave is moving. You can also calculate this with what is called the universal wave equation. This equation can be used for any wave of any type. And the speed of a wave can be based on the frequency and the wavelength of the wave. So the frequency, remember, the frequency is related to how many wavelengths can go past a certain point in 1 second. That's the frequency, and lambda is the wavelength itself. So how long or how short the wavelength is. Like, for example, this red wave here has a much larger wavelength than this guy here. Sounds good? Okay. And a frequency, would be if you started here at the beginning and you waited just 1 second to see how much of the wave would go past at that point. Okay. So, ladies and gentlemen, V is the speed of a wave in meters per second. Lambda is the wavelength in meters. And frequency is the speed in hertz. Or you can also use seconds to the power of -1 or 1 over second. Either of the three is fine. And as I mentioned, it's the universal wave equation. It is also on your data sheet under the section that says waves And it is right there in the wave section. Sounds good? Okay. So what did the one ocean current say to the other ocean current as it went past? Nothing. It just waved. All right. So, ladies and gentlemen, let's do a few calculations. So, a wave has a speed of 0.5 meters per second and a wavelength of 2 meters. Okay, what is its period? Well, ladies and gentlemen, we looked at nothing with the period of a wave, but our equation with it, look at this. Remember this equation? This equation gets used a lot with waves. So I can calculate the frequency and then use this. I have speed and I have lambda. So V is equal to F lambda. I can rearrange that guy. So my first step is going to be, take this equation, I'm going to rearrange it and to calculate the frequency. So as speed over wavelength, so the frequency is 0.5 meters per second divided by the wavelength of 2 meters. And I'm going to be left with a frequency of 0.25 hertz. My second step is I'm going to need to calculate the period, which is take the inverse of the frequency. So 1 over 0.25, and that is going to give me, with appropriate sig digs and units, 4 seconds. Not too bad, eh? Not too bad. All right. So let's look at this one. So this one's kind of fun. Earthquakes. So what did, I'll say the pun afterwards. We'll say the pun now. So what did one tectonic plate say to the other when it bumped into it? Oh, sorry, my fault. Get it? Fault? A fault line is a crack in the crust, and it's where the fault lines rub and move is where you get earthquakes. My fault? Yeah. Okay. So, ladies and gentlemen, an earthquake can produce 2 types of waves, P waves and S waves. And if an earthquake occurs 50 kilometers away from a city, if the P waves travel at 7 kilometers per second and the S wave travels at 5 kilometers per second, calculate how much sooner the P waves reach the city before the S waves. Okay, so ladies and gentlemen, we need to be very, very careful with this. The biggest mistake that I see with these wave calculations is people using the distance that a wave is traveling as the wavelength, or vice versa. So you need to think very carefully. So an earthquake occurs 52 kilometers away from a city. Is that distance from the source of the waves, or is that the wavelength? That's the distance. I did not say the word wavelength. So you have to read the question super carefully, okay? So this is 52 kilometers. The P waves travel at 7 kilometers per second. So the velocity of the P waves is 7 kilometers per second. The speed of an S wave is 5 kilometers per second. Okay, how much sooner will the P waves reach the city before the S waves? So we're trying to find the delta time, the change in time. Okay, the time difference between the waves. So we need to first figure out how long it will take the P waves to travel 52 kilometers and the S waves. Now I want you guys to look at the units here. We have units of kilometers and we have units of kilometers per second. These are equivalent. If I just use these units as they are in the V equals D over T equation, that means that I will get my answer in seconds, and these units will cancel. Okay? Okay. So I'm trying to find time, and so V equals D over T. I need to rearrange this. I swap the place of D and T, or D and V, excuse me. So my equation is T equals D over V. So the time it will take the P wave to travel, the 52 kilometers, speed is 7 kilometers per second. Now look at this, guys, kilometers by kilometers. The kilometers will cancel. That's why I don't have to convert, because the units are consistent. So I put that in my calculator, and I'm going to get 7.4285 seconds. Pretty fast wave. And the time of the S wave, same equation. They're traveling the same distance, so 52 kilometers, but one is traveling at 5 kilometers per second. Note those units. Those units cancel. They're equivalent. It's all right. The only units left are seconds. So the time for the S wave is 10.4 seconds. I have been asked to calculate the delta T, so we want to find the time difference here. So I'm going to take my 10.4 seconds, I'm going to minus it by my 7.4285. Use all those numbers in your calculator, please, and thank you. And once you have your sig digs and your units, you're going to have, after you've done your rounding of that 2.97, you're going to wind up with a delta T, so a time difference of 3 seconds. Sounds good? So the math is not overly hard for this equation. The calculations themselves aren't the hard part. The hard part of this one is trying to determine if and what you need to use. What is the question asking? How do we set up your equation? That's the hard part. Okay. While floating on a tube on a lake, that sounds pretty nice. That could be fun. You note that you bob up and down 40 times in 5 minutes. Okay. You estimate the distance between the crests is 4 meters. What is the estimated speed of the water waves? Okay. Notice how I worded this. Distance between the crests. What is that? It's not D. That's lambda. Okay. I made a very specific reference to the location on a wave, the distance between the crests of a wave. And the distance between the crest of the waves is the wavelength. Okay, so that's 4 meters. You go up and down 40 times in 5 minutes. Okay, well, ladies and gentlemen, we can use that to calculate the frequency. So the definition of frequency is like RPM, rounds per minute. That's another unit for frequency. So the number of times that you bob up and down, 40 times in 5 minutes. Okay. Well, those aren't the right units. We want the units in seconds. Okay. So I need to convert this. I need to convert that to seconds. Okay. Well, 1 minute over 60 seconds, I want to cancel those minutes. 60 on the bottom. I want seconds on the bottom for hertz because 1 hertz is second over -1, right? Okay. So once I plonk that in my calculator, my frequency is 0.13 repeating hertz. Sounds good? Good. Well, I've given you the wavelength. We've now calculated the frequency. Well, what's the estimated speed of the water waves? We can use our universal wave equation. So the speed is equal to the frequency. So using all numbers from your calculator, multiplied by the wavelength, which I gave you in the question. And once you multiply that together, you get 0.53. Repeating. Give it correct sig, digs, and units. And there you go. Sounds good? So once again, the most difficult part about these questions is not the math. It is figuring out, well, what do I have? How can I use it? What is it actually giving me? So that's the tricky part. All right. So, ladies and gentlemen, we've got one more question left, and this is some theory. All right, so a teacher creates a wave in a rope which is fixed at one end to a wall by sending pulses through the rope by simply moving her hand and flicking the rope up and down. What would happen to the wave's amplitude, so how high the wave is, and speed of the wave if the teacher puts more energy into the wave without changing the frequency of the hand's vibration? Okay. So frequency is staying the same, but if we have more energy, okay? So remember, amplitude is how loud it is. So if I was going to swing a rope by doing this, if I was to put more energy in, I would be doing this and not changing the frequency. To put more energy in and change the frequency, you would move your hand faster and faster and faster with the rope, okay? Whereas if I'm going to put in more energy, you move your arm like that when flicking the rope, okay? So for this one, the amplitude is going to increase. However, the speed, ladies and gentlemen, what does the speed depend on? The speed depends on the medium. So the amplitude will increase, but the speed is going to stay the same as the medium doesn't change. Okay, the rope itself is the medium that the wave is traveling through, and the teacher hasn't changed out the rope she's using. So therefore, the speed is not going to change. Okay, so for B, describe what would happen if the wave's frequency and speed, if the teacher puts more energy into the wave by increasing how fast her hand vibrates up and down. Well, with this one, in this case, the frequency is going to increase. But what again? What's not changing? Speed. The speed will stay the same. Okay? Because the medium isn't changing again. Okay? And speed of a wave depends on the medium. Okay. So, ladies and gentlemen, however, though, what will also change is the wavelength. If the frequency gets higher in a wave, so if the speed stays the same and the frequency increases, the wave itself is going to get smaller. So therefore, the wavelength is going to get bigger. Okay, sounds good? Okay, so ladies and gentlemen, here are some practice problems for you guys to try. The green ones are some intermediate level questions, and then those 11 and 12 on page 282 with the excellence. Give a couple of those a try, and then, ladies and gentlemen, we will be back for our next video on resonance. Well, I hope that lesson will resonate with you. Had to happen. All right, have a good afternoon, guys, and I will talk to you all later. No fires, injuries, or explosions. Bye.